We discussed random variables, discrete and continuous, and we have seen what is probability mass function and density function and all. Now let us see what is the solution to this problem. So there is a problem on probability distribution. So we need to write the probability distribution of x, where x represents the number of defective mangoes. So the 5 defective mangoes are accidentally mixed with 20 good mangoes. So there are 5 defective mangoes and 20 good mangoes, and these were mixed. So total there are 25 mangoes. And by looking at them, it is not possible to differentiate between them. It means just by seeing we cannot tell which one is a good one and which one is a defective one. So 4 mangoes are drawn at random from that lot. Find the probability distribution of x, where x represents number of defective mangoes. And what is our random experiment? Random experiment is to draw 4 mangoes, or is to select 4 mangoes. Out of 25. So the number of defective mangoes out of 4, it can be 0. So let me write the possible values of x. Possible values of x are, it can be 0, 1, 2 and 3 and 4. So these are the possible values of x. So now let us see what is the probability distribution of these 5 values. So probability that x equal to 0. So it means we don't want any defective mango to come in this selection. So how many of them you are selecting? You are actually selecting 4 out of 25. So there are only 20 good mangoes. So 20 choose 4 by 25 choose 4. So this is the probability that x equal to 0. Okay, we need to simplify. Next, let me see what is the probability that x equal to 1. So this time we want 1 defective mango and the rest 3 to be good ones. So there are total 5 defectives, out of which I need to select 1 into, and there are 20 good ones, out of which I need to select 3. So 25 choose 4. So similarly, next probability that x equal to 2. So 5 choose 2, 20 choose 2 by 25 choose 4. And next probability that x equal to 3. So that is 5 choose 3 into 20 choose 1 by 25 choose 4. You try to simplify them and write the final expression, okay? So probability that x equal to x equal to 4. That is 5 choose 4 by 25 choose 4. So we want all 4 to be defective mangoes. But that's not a good selection, right? Nobody wants probability that x equal to 4 here. Okay, so this is how you can simply do it. So finally you can write the probability distribution in a table. You write x here and you write p of x here, and here x equal to 0, 1, 2, 3, 4, and you write the probabilities here, the respective probabilities. Okay. Now let's look at one more. So there are 6 red balls and 4 white balls. So total there are 10. 3 balls are it's not known, drawn at random. So obtain the probability distribution of the number of white balls. I hope there is no difference between the previous problem and this problem. So I am leaving it to you. Okay. But here it is not known, it is actually drawn. It's a mistype, typo error. Now here is a problem on continuous random variable. So we know that a discrete random variable is going to have a probability mass function, whereas a continuous random variable is going to have a probability density function. So here the probability density function is given and they are asking us to find these respective probabilities, right? So if you recall the yesterday's thing, if you know f of x is the probability density function, then we know how to calculate probability that a less than or equal to x less than or equal to b. So this can be calculated like this: integral a to b f of x into dx. So this is the formula, you need to use it here, that's it. And you can note down two more formulas, like probability that x less than or equal to a. It means integral minus infinite to a f of x into dx. Whereas other one, probability that x greater than or equal to a, so that is integral a to infinite f of x into dx. Here, if you have a continuous random variable, we take probability that x equal to a, this to be 0. Why? Because when it is continuous random variable, like talking at one point, it doesn't make sense. If you want to talk in neighborhood around a point, it means what you can do is you can talk about this probability that a minus epsilon is less than x is less than a plus epsilon. So remember one thing, in a continuous random variable, we always treat probability that x equal to a to be 0. Why? Because if you see it from the integral a to a f of x into dx, we treat this to be 0. Okay. So now in continuous case, it doesn't matter whether you keep less than or equal to or just strictly less than. Okay. Right. So now let us see what is the answer to the first one. The question is, what is the probability that all of the 3 such tubes in a given radio set will have to be replaced during the first 150 hours of operation? So what is given here? The life in hours of a certain part of a radio tube is given, and whose probability density function is given. So now you can see that x is a random variable which represents lifetime of a radio tube. So the first question they are asking, what is the probability that this lifetime will be less than 150 hours? So they are asking that what is the probability that it is going to be replaced during the first 150 hours? So if you want to replace during first 150 hours, it means it should fail before 150 hours, isn't it? It means probability that x less than or equal to 150. This is what they're asking. You can take strictly, not an issue. So this is what, according to the formula, integral minus infinite to 150 f of x into dx. But you know the function is non-zero from 100 onwards. You can see it here, from 100 onwards only it is non-zero. So this is 100 to 150 and the function is 100 divided by, is that x square or x cube? X square into dx. Now it's a simple integration, 100, and integration of 1 by x square, what will it be? Negative 1 by x. So the limits are from 100 to 150. So this is what I have. So 100 into negative 1 by 150 plus 1 by 100. So if you simplify this guy, in the denominator I'll have what is it if you simplify? You can take 10 out from the denominator, right, and you can cancel it, so you'll have 10. And of course you can take 5 out. So when I take 5 out, so this is how I can do it simply. 100 by, so what I'll do is I'll take 50 out. So if I take 50 out, I have negative 1 by 3 plus 1 by 2. And now this is 2, the LCM is 6, negative 2 plus 1, sorry, negative 2 plus 3. So this will give you 2 by 6, that is 1 by 3. Okay, so now this is the probability that one of the radio tubes will be replaced within first 150 hours. But the question is probability that all of 3 such tubes will be replaced within 150 hours. So we did it for only one. So how about the rest 2? See, you can take the lifetime of one tube is independent of the lifetime of the other tube. Since they are independent, so the final probability is going to be, so the required probability, that's equal to probability that the first tube works less than 150 hours into probability that the second tube and the probability that the third tube. So that's equal to 1 by 3, 1 by 3, 1 by 3. So that is going to be 1 by 27. This is what. Right. And the next question. What is the probability that none of 3 of the original tubes will have to be replaced during the first 150 hours of operation? I hope you can directly see it is exactly the reverse of the first question. In the first question, we want to replace all 3. And in the second one, we don't want to replace any one of them. So none of the three of the original tubes will have to be replaced. So it is easy to answer the second question. So answer to the second question, this is actually 1 minus probability that x less than 150 whole cube. So this is what the required probability. So that's equal to 1 minus 1 by 27. So this is 26 by 27. So this is the probability. Okay, I hope you understand. And the next one, what is the probability that, hello?
Sir, but in key there are different answers, sir.
If there are?
Sir, key అంటే ఆ ప్రాబ్లమ్స్ కి కీ ఇచ్చాడు కదా సార్ కింద ఆ కీలో డిఫరెంట్ వాల్యూస్ ఉన్నాయి సార్.
Okay, let me check. Okay, so here they just gave one third. See, the problem is they didn't do it for 3 tubes. Actually the answer must be 1 by 27 only for the first one. It's a mistake. It's not 1 by 3. It must be 1 by 27. Maybe, but this one, just a minute. For the second one, I think I am wrong. What is the probability that none of the 3 original tubes will have to be replaced during the first 150 hours of operation? Yeah, there's a mistake in my calculation. I can't say that the second statement is exactly opposite of the first statement. Why? Because here there is something in between these two. It's not opposite of one is not the other. So the first question is about replacing all three tubes. Okay, if you don't want this to be happen, then what is the other ways? It may happen that only one tube may be replaced, okay, or maybe two tubes may be replaced, or no tubes will be replaced. So this is the opposite of the first statement. Okay, but here if you look at the second case, this is just one of these three. So the second one is just one of these the opposite cases. It's not full of it. Okay. So therefore I cannot calculate it in this way. 1 minus of if I take 1 minus of this, then it is taking care of all these possibilities. The possibilities are none of the tubes are going to be replaced, only one of the tube is going to be replaced, or only two of the tubes is going to be replaced. So it is taking care of all of them. But I don't want to take these two, 1 and 2. So now to answer this question, let us go this way to answer the second question. So if you take the fastest tube, what is the probability that it's not going to be replaced within 150 hours of operation? So that's what exactly probability that x greater than 150. This is what I have to calculate. Okay, so now this one you can write it as 1 minus of probability that x less than or equal to 150. You know why? Why? Because we know that sum of probability that x. Okay, we are talking about continuous case. Let me discuss this. Integral minus infinite to infinite f of x into dx. This is equal to 1, where f of x is a probability density function. Where f of x is a probability density function. So this is the property, right? So now this property can be written this way: integral minus infinite to a f of x into dx plus integral a to infinite f of x into dx, that is equal to 1. Now if you look at the first expression, that's what probability that x less than or equal to a. But in continuous case, it doesn't matter whether you write equal to or not, plus, and this one you can see it as probability that x greater than or equal to a. Okay, so this will give you 1. So this implies probability that x greater than a can be expressed as 1 minus probability that x less than or equal to a. Okay. So now using this formula, I'm writing this expression. Probability that x greater than 150 is nothing but 1 minus of probability that x less than or equal to 150. And we already calculated this. This is 1 minus 1/3. So this is actually 2/3. So this is the probability that first tube not going to be replaced. Within first 150 hours of operation. So here probability that x greater than 150 can be written as 1 minus probability that x less than or equal to 150. Why? Because here you can see the justification. This is the property of the probability density function, and using it we express this way, right? So finally we calculated what is probability that x greater than 150, And now we want probability that none of the tubes are going to be replaced. So it means for each tube we know that probability is 2/3. So there are 3 tubes and they are independent. So 2/3 into 2/3 into 2/3. So that will be 827. Right. Okay. Now how about this third one? What is the probability that a tube will last less than 200 hours if it is known that the tube still functioning after 150 hours of service? So after 150 hours the tube is still working. Now what is the probability that it is going to fail before 200 hours? That's the question. Now this is about a single tube only. So now it is enough to see what is the probability that 150. I hope here you'll get the conditional probability. Why? Because it is given something, it is working after 150 hours. So what is the probability that x less than or equal to 200 given that x greater than 150? This is what they're asking, right? What is the probability that tube will last less than 200 hours if it is known that the tube still functioning after 150 hours of service? So they're asking conditional probability. So here let us, we know the formula probability that A given B, which is nothing but probability of A intersection B divided by P of B. This is what, right? Now I need to see what is the intersection of x less than or equal to 200 and x greater than 150. X less than or equal to 200, let's say this is 200 and you're taking this lower part, and x greater than or equal to 150. Let's say this is 150 and above. So now you can see the intersection is exactly this 150 to 200. This is the intersection, right? So therefore, probability that x less than 200 given x greater than 150, can I write it like this? Probability that 150 less than or equal to, less than x less than 200 divided by probability that x greater than 150. Do you agree? So we already know what is probability that x greater than 150. That is 2/3. We calculated it, which is 2/3, and it is enough to calculate the first expression, so the numerator expression. So let me do that. 150 less than x less than 200, that's going to be integral 150 to 200. This is 100 divided by x square into dx. So 100 is common, the derivative integration is minus 1 by x. So minus 1 by 200 plus 1 by 150. So you can take 50 common. So 100 by 50, and here I have minus 1 by 4 plus 1 by 3. And this will be 2 times LCM is 12, negative 3 plus 4. That's equal to 1/6. Okay. So now we can answer it. So the numerator is 1/6 and the denominator is 2/3. So this is equal to 1/6 into 3 by 2. So that's what exactly 1 by 4. So this is the probability that the tube works less than 200 hours, given that it is working after 150 hours. Let us look at the last part. So what is the maximum number of tubes that may be inserted into a set, so that there is a probability of 0.5 that after 150 hours of service all of them are still functioning? It seems interesting. What is the maximum number of tubes that may be inserted into a set, so that there is a probability of 0.5 that after 150 hours of service all of them are still functioning? It means we want probability that x greater than or equal to 150. That equal to, it's not directly equal to 0.5. So if there are 3 tubes, so probability that the 3 tubes are still functioning after 150 hours is cube of this expression. So if there are n tubes, then I have to take power n. So let me assume that, suppose that maximum number is n. Suppose that there are n tubes. So there are n tubes, therefore probability that all are going to work after 150 hours. So let me write. After 150 hours, that's equal to probability that x greater than 150 whole power n, because their lifetimes are independent of each other. So now we want this probability to be greater than, that is exactly equal to 150, right? Maximum number of tubes that may be inserted into the set, so that there is a probability of 0.5. So this is what we want. So probability that x greater than 150, this whole to the power of n, we want this to be equal to 0.5. Now the question is, what is n? And we know this expression, probability that x greater than 150, which is actually 2/3, so 2 by 3 whole power n, which is equal to 0.5. Now you can apply logarithmic function on both sides, so n into log of 2 by 3, that's equal to log of 0.5. So now therefore you can see what is n. N equal to a log of 0.5 divided by log of 2 by 3. What is it if you calculate?
$1.70.
So you're saying 1.70, okay. So 1.70, so this is approximately 2. So 2 tubes are enough, so that this probability is equal to 0.5. So the maximum number of tubes are 2. Okay. So this is how these problems can be solved using probability density function. But here the most important thing is to understand the problem, what they are asking. Right. Now let me talk about one more important topic, which is cumulative distribution function. And before that, just let me discuss about the graphs of probability mass functions. Suppose if you have probability mass function, their distribution can be drawn like this. See, for example, let me take some distribution here. So this is the probability distribution I'm taking. So here I'll take the random variable x, whereas here I'll take the probabilities p of x. Okay, so the random variable is taking the values 0. See, just for clarity, I'd like to take -1 here. It's not actually the y-axis. It is just one line which is left to the y-axis. And here it is 0, and here it is 1, and here it is 2. Okay, so now the maximum, let me suppose this is 1, and this will be 0.5, and somewhere here 0.3, and somewhere here 0.2. Now the random variable x equal to 0, which is assigned to 0.3, here it is, and 1 is assigned to 0.2, and next 2 is assigned to 0.5. Okay, now this is the probability distribution. If you want, you can take them like this, just for identification. So similarly, if you have some other distribution, you can take x values here and probabilities here, and you can plot them. Okay, so when it comes to probability density function, so the probability density function, so here we'll have x, we'll take the random variable x, and whereas here we take f of x. And remember one thing, this f of x value, no need to lie between 0 and 1. Okay, this is just the probability density function. For example, so you have a continuous distribution which is distributed from, let's say, 0 till 0.5 only. Let me assume this is 0.5. Okay, so now I'll show you some distribution. So let's say this is 1 and this is 2. Now my distribution function is this, just this. Let me write this function explicitly so that it will be clear. Now my function is f of x equal to, this is 2 when 0 less than x less than 0.5, and whereas this is 0 otherwise. Okay, so before 0 it is 0, before 0 the function is 0, and at 0 it goes to 1, and after it goes to 2, and it will continue on 2 till 0.5, and then after it comes down and it continues here at 0. And you could see that this function exactly satisfies all properties of probability density function. You can see integral minus infinite to infinite, f of x into dx, this will give you 1, and f of x is greater than or equal to 0. Okay, these are the two things I needed for a density function. Okay, so now this is a probability density function of a random variable. So here what you should understand is the area under the function is 1, but the function values, it can lie at any range, but it cannot take negative, it can take any positive value, in such a way that the area under the function becomes 1. That's what. Okay, so this is what about the probability density function. Now we are going to create a new function based on these mass functions and as well as density function. So here my interest is to see what is the probability up to 1. It means this is what is my interest, probability that x less than or equal to 1. And similarly, what is the probability up to 2, that is x less than or equal to 2. It means if you want to find x less than or equal to 1, you have to do this, probability that x equal to 0 plus probability that x equal to 1. In this case, because you need to take care of 1 and as well as the part which is less than that, which is only 0. So these two. Suppose if you say probability that x less than or equal to 2, it means p of x equal to 0 plus p of x equal to 1 plus probability that x equal to 2. Okay, so what you are doing is you are accumulating all probabilities up to this point, up to 2 or up to 1. Similarly, in continuous case also you can do that. Let's say from 0 to up to 0.25 I'd like to accumulate all the probabilities. So what I'll do is I'll take area of this part. So this is what exactly probability that x less than or equal to 0.25. Now the notation is going to be integral minus infinite to 0.25 into f of x into dx. Right? Now, so now let us give name for this function which is taking cumulative probabilities. So let me define it here, cumulative distribution function. Cumulative distribution function. And this is how it is defined. And we are going to denote it with capital F of x. So capital F of x is equal to probability that x less than or equal to a. Either it is continuous or discrete, whatever it may be. So this is the cumulative distribution function, probability that x less than or equal to a. Okay, suppose if x is a discrete random variable, so then probability that, f of x is equal to, sorry, what I am writing here, it's not f of x, this is actually f of a. F of a is equal to probability that x less than or equal to a. Okay, so now let me write what is f of a for a discrete random variable, that is probability that x less than or equal to a, which is equal to summation of probability that x equal to I, where I is from I less than or equal to a. It means up to a you need to add all probabilities before that. So this example you can see to understand it. Since the possible values of x are 0, 1, 2, you are taking care of just 0, 1 and 2, that's it. Suppose if it is taking negative 1, negative 2, negative 3, yes, that also you can take care. So next, if x is continuous random variable, if x is a continuous random variable, so then the probability, cumulative distribution function, this is how we'll write cumulative distributive function, that is f of x, f of a, which is equal to probability that x less than or equal to a, that's what exactly, integral minus infinite to a f of x into dx, where f of x is the probability density function of x. Okay, so here you can do one thing, you can obtain a density function with the help of distribution function. If you observe that the integration of density function is distribution function. So now if I take the derivative of distributive function, it means d by dA of f of a So the derivative of the distribution function. So that's what d by dA of integral minus infinite to a f of x into dx. And you have studied Leibniz rule and as well as fundamental theorem of integral calculus, and that says the derivative of this integral is nothing but f of a, isn't it? So therefore the relation between the cumulative distribution function and the probability density function is this: derivative of cumulative distribution function, which is nothing but the density function, or we can write it this way: f dash of a is nothing but f of a. So I hope it is clear to you, and let me know if you have any questions or doubts. So in the next class we'll talk about mathematical expectation. It means when you perform a random experiment, you are defining a random variable. So what is the expected value of the random variable? Like when you toss a coin for 100 times, so how many heads you are expecting? Let's say if your random variable is number of heads. So that's what we'll discuss in the next class: mathematical expectation and variance. Okay, so here I'll stop it. Let me know if you have any questions or doubts.